In this lesson, we are going to find the turning point and work out whether something is a maxima or a minima using calculus. Okay, so the turning point is this point right there. It's when it stops having a negative slope and starts having a positive slope. Somewhere in the middle, it's going to be flat. So the rule is for a turning point always happens when the gradient equals 0, i.e. when it's flat. It's not a great drawing of a flat thing there, but it's where there is no slope. Okay, and then we're going to do the second derivative test, and the second derivative test will tell us whether something is a maxima or a minima. Okay, so we need to find the gradient. So what we're going to do is we're going to differentiate this. We always differentiate when we want to find the gradient. So if that's the original function, then dy dx is going to be 2 times 3, which is 6, x, and then 1 times -2 is -2, and that the x disappears, and this is annihilated, the +1. What do we do then? Well, we find out the value of x where this equals 0. And it's going to be fairly trivial. We're going to add 2 to both sides. So 6x equals 2. So x therefore must be equal to 2 over 6, which is 1/3. And if you look, yep, it is about 1/3. Well, it is exactly 1/3. Here is a half there. There's a half. So that's going to be at 1/3. What's going to be the value there? Well, we're going to go back into the original function here and put in 1/3. So 3 times 1/3 squared minus 2 times 1/3 plus 1. And I don't know what that is off the top of my head. Let's work it out. Let's work it out. So 3 times squared minus 2 plus 1, 2/3. Okay. Yeah, I guess it would be 2/3. So it has a turning point at 2/3. And that kind of makes sense. If that's 0.5 and that's 1, that's about 0.66666. So it has a turning point at 1/3, 2/3. Okay. Is this a maxima or a minima? Well, just looking at the graph, we can see that it's a minima. It goes down to a minimum point and then starts coming back up again. How could we prove that? Well, we prove it by looking at it, but there is a test, and it's the second derivative test. What that means is that we differentiate this again. So we take this, we differentiate it again. So if dy dx is 6x minus 2, when we differentiate that again, and it's going to be dy2 dx squared. I don't expect you to know that notation. When we differentiate that, that's just going to become 6, and this 2 is, that -2 is going to disappear. So when we differentiate it a second time, we get positive 6. Now, if the second derivative is greater than 0, i.e. it's a positive number, it is a minima. And if the second derivative is less than 0, i.e. it's a negative number, it is a maxima. And there is no local maxima on this graph. It's a parabola. Parabola only has one hump. So therefore we can work out, we can say using calculus that this has a minima at when x equals 1/3 and y equals 2/3 at that point. Okay. We're going to do exactly the same for this one. If these look familiar, these are the same graphs that we graphed in the last lesson. So for this one, I want to know what are the turning points. So where are the turning points, and are they maximum or minimum? Maxima or minima? Well, just looking at it, we can see that this point here is a maxima point, and this point here is a minima point. But say we didn't know that, we couldn't graph it. How could we find out what those points are? We do exactly the same as we did in the last question. So we've got y equals 3x minus 4x. We differentiate that. We differentiate y with respect to x, and we get 3 times 1 is 3. X, the 3 loses 1, becomes 2x. And minus 4x becomes minus 4. We set that equal to 0. And notice this is a parabola when we differentiate that. So there's going to be 2 solutions. And we know that there are 2 turning points. There's a maxima and a minima on here. So then we would solve that. So then we would probably go to our calculator and solve it. So we would find the solutions for that using the polynomial solver or some other algebraic method, but I'm too lazy at the moment to do that. So it's 3x squared plus 0x minus 4. And it's going to have the solutions 1.155 and negative 1.55. Negative 1.155. How would we find out the y coordinates for that? We will put that into the original equation. So this is going to be 1.155 cubed minus 4 times 1.155. That's going to give us this one here. And for this one here, we're going to put, this is going to be equal to negative 1.155 cubed minus 4 times 1.155. And I'll leave you to find the exact number for that. How do we work out which one is the maxima and which one is the minima? We're going to differentiate it again. So we're going to take this thing here and we're going to differentiate that a second time. So we take 3x squared minus 4 and we want to differentiate that. So 2 times 3 is 6, x to the power of 1, and the constant disappears. So d2y dx squared is that, the second derivative, which I guess you could say, you could write that as that. What do we do then? Well, we're going to take one of these numbers, put it in here. So we know that 6 times 1.155, I don't need to know the exact number, I just need to know that it's greater than 0. So that's going to be the minima there. And 6 times negative 1.155, I don't need to work out the exact number, I know that that's a number that's less than 0, so that must be the maxima there. And that kind of makes sense. So we know that there is a maxima where x equals negative 1.155 and a minima where x equals positive 1.155. I think I may have contradicted that a bit earlier on, but that's what they are. I think that one probably. Okay, so it is kind of counterintuitive. Something, if the second derivative is greater than 0, it's a minima. If it's less than 0, it's a maxima. All right, let's do another example. All right, this one. So again, this is one of the ones that we solved last time. So we can see just by inspecting it that there is a maxima there, local maxima, and a minima there, and a minima here. How do we work out where exactly they are? Well, we're going to differentiate this. Let's actually say that it's not y. Let's call it f of x, so you can see that these notations are swappable. If we differentiated that again, f dash of x is going to be 4x cubed. The 4 comes out the front. The 4 loses 1. 2 times negative 3 is negative 6. X to the power of 1, and the constant annihilates, it goes to 0. So that tells us that when we set that equal to 0 and solve, we can work out what these 3 points are. And we can see just by looking at it that we factor out the x. So we know that x equals 0 is a solution, which kind of makes sense because here's x equals 0 and it's going to be there. And we worked it out before it was 1. So therefore we will want to find 4x squared minus 6, set that equal to 0 and solve. So let's actually do a little bit of algebra. Let's add 6 to both sides. So 4x squared equals 6. X squared equals 6 over 4, which is 3 over 2. So therefore x must be equal to plus minus the square root of 3 over 2. So therefore our 3 solutions are when x equals positive square root of 3 over 2 and when x equals the negative square root 3 over 2 and 0, of course. How do we work out whether they're maxima or minima? We're going to differentiate it again. So we worked out before that f dash of x from up here is 4x cubed minus 6x. So therefore f dash dash of x must be 3 times 4, which is 12x squared minus 6. Okay, if we put in a 0, so f dash dash, and we set x equals 0, we're going to get 12 0 squared minus 6, which is negative 6. Now negative 6 is less than 0, so therefore this must be a maxima, and sure enough we have a maxima here. If we put in negative 3 over 2, so negative square root 3 over 2, okay, we're going to have 12 times negative square root 3 over 2, which is going to be a positive number, minus 6, and it's still going to be a positive number. In fact, let's grab a calculator just to prove it. Um, 12 negative 6 is a positive number, so therefore they must be minima. There is a minima here and a minima here. Just as a sort of test, let's put in the original equation into our graphing calculator. Oh, it's still there from the last question. Okay, so that's there, and we want to g-solve. We want to find the maxima, the local maxima. It's there, 0, 1. There we go, we found it. And then we want to g-solve again. We want to find the minima. First minima is there, and I invite you to work out that that is indeed the square root, the negative square root of 3 over 2. And this is going to be the positive square root of 3 over 2. That's how that's done. All right, we'll do one more. So we can look at this graph and we can see that there is a maxima there and a minima there. Okay, but let's prove it and let's work out exactly where they are. So again, I'm going to sort of change the notation so you can see that it's exactly the same. So if f of x is that, f dash of x is going to be 3 times 2, which is 6, x, and the x loses a power. 2 times negative 3 is negative 6, x, and there's a 1 in front of it there and a 1 there, so that's going to be equal to 1. We would set that equal to 0 and solve. Okay, but we did that last time. Let's differentiate that again a second time. So 2 times 6 is going to be 12. X minus 6, and that 1 is going to annihilate. Well, we know that we have a turning point here at negative, I think it was 0.6 or something, negative 0.6. Well, 12 times negative 0.6 minus another 6 is definitely a number which is less than 0, so therefore it's a maxima. And for this one here, we know that it's positive 6, so 12 times 0.6 minus 6, which is, look, that is a number greater than 0, so therefore that is a minima. So this must be a minima here, this must be a maxima here. So let's sort of sum up. To find the turning point, we differentiate and then set equal to 0 and then solve for x. Noticing that there can definitely be more than one turning point. Then we differentiate again and put in the values of x from here. And if the second derivative is less than 0, it's a maxima. If the second derivative is greater than 0, it's a positive number, it's a minima. And you should be asking yourself the question, what if it equals 0? Is it still a turning point? And the answer is yes, it is still a turning point. It's what's called a saddle point at that point. So a saddle point is a point where the graph is going sort of up like that, and then it goes flat, and then it starts going back up again. That's a saddle point. Or it could be going down and then flattens off, and then it starts going back down again. That's also a saddle point. They're rare. You're much more likely to have those. In fact, I don't think you'd even get an example of a saddle point in your exam, but that's what happens when f dash dash of x equals 0. Okay, if you have any questions, do comment and I'll answer all your questions in a future lesson. But until then,